Welcome to DAR Tutors for online and home tuition. Today, we're going to explore two fundamental topics in functions: rational functions and composite functions. By the end of this session, you will be able to, first, analyze and graph rational functions. Second, define and evaluate composite functions. These concepts are crucial for your IB mathematics, applications and interpretation higher-level exams. Let's begin with rational functions. First, let's establish what a rational function is. You're already familiar with linear and quadratic functions, which are the simplest examples of a larger family called polynomials. Polynomials can be written in this general form, where you have a sum of terms, each with a constant coefficient and a variable x raised to a non-negative integer power. A rational function is simply one polynomial divided by another. We can represent it as f of x equals p of x divided by q of x, where p and q are both polynomial functions, and the denominator q of x is not the zero polynomial. We'll start with the simplest type of rational function, which is a reciprocal function. A reciprocal function is of the form y equals k over x, where k is a non-zero constant. These functions have a characteristic graph called a rectangular hyperbola. Let's examine the most basic example, y equals 1 over x. Here we have the graph of y equals 1 over x. Notice two key features. First, the graph has two separate branches. Second, it never touches or crosses the x or y axes. This brings us to the concept of asymptotes, which are lines that the graph approaches as the x or y values move towards infinity. For y equals k over x, we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Let's formalize our understanding of these asymptotes using limits. Consider the function y equals 1 over x. The domain of this function is all real numbers except x equals 0, because you cannot divide by 0. As x approaches 0, the function's value approaches infinity, which is why we have a vertical asymptote there. Specifically, as x approaches 0 from the right side, which we write as x tends to 0 plus, the value of 1 over x tends to positive infinity. Conversely, as x approaches 0 from the left side, or x tends to 0 minus, the value of 1 over x tends to negative infinity. Now let's look at the horizontal asymptote. This occurs as the absolute value of x becomes infinitely large. As x approaches positive infinity, the value of 1 over x gets closer and closer to 0, remaining positive. We write this as 1 over x tends to 0 plus. As x approaches negative infinity, 1 over x also approaches 0, but it remains negative. So we write 1 over x tends to 0 minus. The horizontal asymptote is y equals 0. So we've now discussed and formalized the asymptotes for the basic reciprocal function y equals 1 over x. Let's investigate how the constant k affects the graph of the reciprocal function y equals k over x. For this, we'll consider two cases: when k is positive and when k is negative. First, let's look at the case where k is positive. Here we have the graphs of y equals 1 over x, y equals 2 over x, and y equals 4 over x. All of them have branches in the first and third quadrants, with the same asymptotes at x equals 0 and y equals 0. What is the effect of increasing k? As k gets larger, the function's values for a given x also get larger. This means the branches move further away from the origin, or from the asymptotes. Now let's consider the case where k is negative. Now we're looking at y equals negative 1 over x, negative 2 over x, and negative 4 over x. Notice a fundamental change. The branches have now flipped and are located in the second and fourth quadrants. So if k is negative, the graph is in quadrants 2 and 4. As k becomes more negative, its absolute value increases, which again means the branches move further away from the asymptotes. The sign of k determines the quadrants where the graph lies. Next, let's explore more general rational functions of the form y equals ax plus b divided by cx plus d. These functions are essentially transformations of our basic reciprocal function y equals k over x. Just like y equals k over x, these functions also have vertical and horizontal asymptotes. A vertical asymptote occurs where the denominator is 0. A horizontal asymptote is the line the graph approaches as x tends to positive or negative infinity. For a rational function written in the form y equals k over x plus h plus v, The vertical asymptote is x equals negative h, and the horizontal asymptote is y equals v. But what if the function isn't in this standard form? There are simple rules that apply directly to the general form. The vertical asymptote is found by setting the denominator equal to 0. So, cx plus d equals 0, which gives x equals negative d over c. The horizontal asymptote is found by taking the ratio of the coefficients of the x terms in the numerator and denominator. This gives y equals a over c. It's worth noting that a over c is the same v we saw in the standard form. We'll show this in a worked example, so remembering these two simple rules is key. Let's apply these rules to a worked example. Consider the function y equals 2x plus 1, all divided by x minus 1. Our goal is to analyze it completely and sketch its graph. First, let's find the vertical and horizontal asymptotes. We'll use the general form rules. For the vertical asymptote, we set the denominator to 0. X minus 1 equals 0 gives us x equals 1. For the horizontal asymptote, we take the ratio of the coefficients of x2 over 1, which is 2. So the asymptote is y equals 2. Next, let's find the intercepts. The y-intercept is found by setting x to 0. When x is 0, y equals 2 times 0 plus 1 divided by 0 minus 1. This simplifies to 1 divided by negative 1, which is negative 1. The y-intercept is at the point 0 to 1. The x-intercept is found by setting y, or f of x, to 0. A fraction is 0 only if its numerator is 0. So we set the numerator 2x plus 1 equal to 0. Solving for x gives us x equals negative 1/2. The x-intercept is at the point 1 toward 0. Let's now convert this function to the standard form to see the connection between the asymptotes. We can rewrite 2x plus 1 as 2 times the denominator, x minus 1, plus 3. Splitting the fraction gives us 2 plus 3 over x minus 1. In this form, y equals a plus b over cx plus d. We can see the asymptotes clearly. Y equals 2 and x equals 1, just as we found before. Now let's sketch the graph using all this information. We draw the coordinate axes and our two asymptotes, x equals 1 and y equals 2. We then plot the y-intercept at 0 to 1 and the x-intercept at 1 to 0. Based on the positive value of the term 3 over x1 in the standard form, the branches will be in the top right and bottom left regions relative to the asymptotes. We draw smooth curves through our intercepts and approaching the asymptotes. And that's our completed graph. Sign diagrams are a very useful tool for understanding when a function is positive or negative. For a rational function, we mark two key types of points on the number line: roots, which are where the function is 0, and vertical asymptotes, which are where it's undefined. Let's use our previous function, f of x equals 2x plus 1 divided by x minus 1, to create a sign diagram. We've already identified the roots and asymptotes. The function is 0 at x equals 1/2, and it's undefined at x equals 1. These are our critical points. We start by drawing a number line and marking these two critical points. At the root x equals 1/10, the function's value is 0. We often represent this with a solid line. At the asymptote x equals 1, the function is undefined. We represent this with a dashed line. These 2 points divide our number line into 3 regions. To determine the sign of the function in each region, we pick a test point. In the region x is less than 1/2, let's test x equals 1. The numerator is 1 and the denominator is 2. Negative divided by negative is positive, so the function is positive in this region. In the region between 1/2 and 1, let's test x equals 0. The numerator is 1 and the denominator is 1. Positive divided by negative is negative. The function is negative here. Finally, in the region x is greater than 1, let's test x equals 2. The numerator is 5 and the denominator is 1. Positive divided by positive is positive. The function is positive here. We can now construct our final sign diagram. It clearly shows the function's sign behavior across its domain. The sign diagram shows that the function is positive for x less than 1/2, negative for x between 1/2 and 1, and positive again for x greater than 1. This matches the sketch we made earlier, where the graph was above the x-axis in the positive regions and below in the negative region. Now we transition to our second main topic, Composite functions. This is a powerful concept where the output of one function becomes the input of another. The basic idea is that a composite function applies two or more functions in a sequence. The composite function of f and g is written as f circle g, or FOG. It's read as f following g. This means that g operates on x first, and then f operates on the result. A great way to visualize this is with function machines. Let's say we have two functions, f of x equals x squared, and g of x equals x plus 2. First, x goes into the g machine, which adds 2 to it, giving us x plus 2. This output, x plus 2, then becomes the input for the f machine. The f machine squares its input. So the final output of the composite function is x plus 2 squared. This demonstrates that FOGX means g first, then f. This order is crucial, as we'll see next. A key property of composite functions is that they are generally not commutative. This means that FOGX is almost never the same as GOFX. Let's demonstrate this with an example. Let f of x equal 2x plus 1 and g of x equal 3 minus 4x. We will calculate both compositions. First, let's find FOGX, or f of g of x. We start by substituting the entire function g of x into f of x. So we have f of 3 minus 4c. Our function f says to multiply its input by 2 and add 1. Doing this, we get 2 times 3 minus 4x plus 1. Expanding and simplifying, we find that FOGX equals 7 minus 8x. Now let's calculate the composition in the other order, GOFX. This time, we substitute the function f of x into g of x. So we need to calculate g of 2x plus 1. Our function g says to subtract 4 times its input from 3. So we have 3 minus 4 times 2x plus 1. Expanding and simplifying gives us 3 minus 8x minus 4, which equals negative 8x minus 1. As you can see, 7 minus 8x is not the same as negative 8x minus 1. This confirms that the order in which you compose functions matters a great deal. Sometimes, you may need to evaluate a composite function at a specific numerical value. There are 2 methods to do this. Let's use the example. F of x equals x squared plus 1 and g of x equals 3 minus x. We'll find FOG2. Method 1 is to first find the general composite function, FOGX. As we've seen, this is f of g of x. We substitute g of x into f of x, which gives us 3 minus x squared plus 1. Then we plug in x equals 2, which gives 3 minus 2 squared plus 1. That's 1 squared plus 1, which equals 2. Method 2 is often more efficient. We start by evaluating the inner function at the given number. For FOG2, the inner function is g. So we calculate g of 2 first. G of 2 is 3 minus 2, which equals 1. Now we take this result, 1, and use it as the input for the outer function. So we calculate f of 1, which is 1 squared plus 1, also equaling 2. Both methods give the same answer, but the second method avoids the need to find the full algebraic expression for the composite function. Understanding the domains of composite functions is a critical and often overlooked aspect. The domain of FOGX is not necessarily the same as the domain of fx or g at x. It depends on both. The input x must be in the domain of the first function applied, g. Furthermore, the output of g, which is g of x, must be in the domain of the second function applied. If either condition isn't met, x is not in the domain of the composite function. Let's look at a classic example that often appears in IB questions. Suppose f of x equals x, squared with all real numbers as its domain, and g of x equals the square root of x, with a domain of x greater than or equal to 0. Let's find the composite function f of g of x. This is f of the square root of x, which equals the square root of x squared. We might be tempted to simplify this to just x. However, this simplification is not valid for all x. The original function was f of g of x, which included the g function, the square root of x. For that square root to be defined, x must be greater than or equal to 0. Therefore, The domain of the composite function is not all real numbers, but only x greater than or equal to 0. To be completely rigorous, it is better to write the composite function as f of g of x equals the square root of x squared, where x is greater than or equal to 0. Always remember to check the domains. Composite functions frequently appear in applied contexts. Let's work through an example from physics or engineering. The outside temperature at an altitude a km is given by the function t of a equals 25 minus 6a. The altitude of an aeroplane t minutes after takeoff is a of t equals 12 minus the fraction 60 over the quantity t plus 5. We need to find the composite function t of t and explain what it means. We will substitute the entire function a of t into the t function. So t of t becomes 25 minus 6 times the expression for a of t. We distribute the negative 6, giving 25 minus 72 plus 360 over t plus 5. Simplifying this, we find that the composite function is 360 divided by t plus 5 minus 47. The question also asks us to interpret this new function. The original functions were temperature as a function of altitude and altitude as a function of time. By composing them, the variable a is eliminated. The resulting function, t of t, represents the temperature outside the airplane directly as a function of the time in minutes that has passed since takeoff. Thank you for watching this DAR Tutors video. If you found this explanation helpful and you're looking for expert one-on-one support for your IB, A-Level, or IGCSE studies, we encourage you to contact DAR Tutors. We offer personalized online and home tuition designed to help you build confidence and excel in your exams. Whether you need to strengthen foundational concepts or master advanced problem-solving techniques, our experienced tutors are here to guide you. Reach out to DAR Tutors today to take the next step in your academic journey. Now, let's review the concepts we've covered today with a series of practice questions. You can pause the video after each question to work it out yourself, then resume to see the full solution. Here is your first IB-style question. Consider the function f of x equals the fraction x plus 1 divided by x minus 3. The question asks to find the equations of its asymptotes and determine its domain and range. Pause the video now and try to solve this question. Welcome back. Let's walk through the solution together. Part A asks for the asymptotes. The vertical asymptote is found by setting the denominator equal to 0. So x minus 3 equals 0 gives x equals 3. The horizontal asymptote is the ratio of the leading coefficients. Here, the coefficient of x in the numerator is 1, and in the denominator is also 1. So y equals 1 over 1, which simplifies to y equals 1. Part B asks for the domain and range. The domain includes all x values for which the function is defined. We know it's undefined at the vertical asymptote, x equals 3. So the domain is x is not equal to 3. In set notation, that's the set of all x such that x is in the real numbers and x is not equal to 3. The range includes all y values the function can output. A horizontal asymptote represents a y value that the function approaches but never actually reaches. Our horizontal asymptote is y equals 1. Therefore, the range is y is not equal to 1. In set notation, that's the set of all y such that y is in the real numbers and y is not equal to 1. Here is practice question 2, involving composite functions. Let f of x equal the fraction 2 divided by x plus 1. Let g of x equal the fraction 1 divided by x. We need to find the expressions for both f of x and g of x and determine the domain of each composite function. Pause the video and work through this problem carefully, especially paying attention to the domains. Let's review the solution for question 2. Part A asks for f of x. First, we find the expression f of x is f of g of x. We substitute 1 over x into f of x, which gives 2 divided by 1 over x plus 1. To simplify, we get a common denominator of x, giving us 2 divided by 1 plus x over x. Multiplying by the reciprocal gives us 2x divided by 1 plus x. Now for the domain. The input x must be in the domain of g. The domain of g is x is not equal to 0, 0. Additionally, The output of g, which is 1 over x, must be in the domain of f. The domain of f is all real numbers except for -1. So we need 1 over x not equal to -1, which means x is not equal to -1. Combining these conditions, the domain of f of g x is all x such that x is not equal to 0 and x is not equal to -1. Now for part b, g of x. We find the expression by substituting f of x into g of x. This gives us 1 divided by the fraction 2 over x plus 1. Taking the reciprocal, we get x plus 1 divided by 2. For the domain, x must be in the domain of f, so x cannot be negative. 1. The output of f, which is 2 over x plus 1, must be in the domain of g. The domain of g is x is not equal to 0, so 2 over x plus 1 must not be equal to 0. A fraction is 0 only if the numerator is 0, but 2 is never 0. So this second condition is always met. The domain is therefore just x is not equal to -1. Here is practice question 3, combining rational functions and sign diagrams. The question asks to draw a sign diagram for the function f of x equals the quantity x plus 4 divided by the quantity x minus 1. Then we need to use this sign diagram to solve the inequality f of x is less than 0. Take a moment to work through this sign diagram and solve the inequality. Let's check your solution for question 3. Part A asks for the sign diagram. The root of the numerator is at x equals 4. This is where the function is 0. The vertical asymptote is where the denominator is 0, so x equals 1. These are our critical points. We draw a number line and mark these points. We'll use a dashed line at the asymptote x equals 1 and a solid line at the root x equals 4. This divides the line into 3 regions. We now test a point in each region. For x less than 4, we test x equals 5. The numerator is negative, the denominator is negative. Negative divided by negative is positive. For x between 4 and 1, we test x equals 0. The numerator is positive, the denominator is negative. Positive divided by negative is negative. For x greater than 1, we test x equals 2. The numerator is positive, the denominator is positive. Positive divided by positive is positive. Our final sign diagram is positive for x of 4, negative for 4x1, and positive for x1. Part B asks to solve the inequality f of x is less than 0. We look for the region on the sign diagram where the sign is negative. This occurs between our 2 critical points. So the solution to the inequality is x is greater than or 4 and less than 1. You could also write this in interval notation as or 4, 1. Practice question 4 is a multi-part problem that brings together several of our concepts. Given the function g of x equals the quantity 2x minus 1 divided by x plus 2, we first need to show that its horizontal asymptote is at y equals 2. Then we find its axis-intercepts. And finally, we find the domain of its inverse function, g inverse. Give this question a thorough try. Part A requires the rearrangement into standard form. Let's review the solution for question 4. For part A, we need to show the horizontal asymptote is at y equals 2. We rewrite the numerator. We can write 2x minus 1 as 2 times the denominator, x plus 2 minus 5. Splitting this fraction gives us 2 minus 5 over x plus 2. From this standard form, we can clearly see that the horizontal asymptote is at y equals the constant term, which is 2. Part B asks for the axis-intercepts. For the y-intercept, we set x to 0. G of 0 is negative 1 over 2, so the intercept is 0, 1 thou. For the x-intercept, we set g of x to 0. The fraction is 0 and the numerator is 0, so 2x minus 1 equals 0. This gives x equals 1/2. The intercept is 1/2, 0. Part C is a common IB trick question. Find the domain of g inverse. Recall that the domain of an inverse function is the range of the original function. We found in part A that the horizontal asymptote of g is at y equals 2. This means the range of g is all real numbers except 2. Therefore, the domain of g inverse is also all real numbers except 2. Our final question is a challenging one, testing your understanding of domains of composite functions. Let f of x equal 1 over x and g of x equal x squared plus 3x plus 2. Find the expression for FOGL and then find its domain. This will involve solving a quadratic inequality. This question requires careful attention to detail. Pause the video and give it your best effort. Let's review the final solution for question 5. First, part A, find the expression. We substitute g of x into f of x. The function f is 1 over its input. So, f of x is 1 divided by the quadratic expression x squared plus 3x plus 2. We can factor the denominator to x plus 1 times x plus 2. Now for the crucial part B, the domain of this composite function. Remember the two rules. First, x must be in the domain of g. Since g is a polynomial, its domain is all real numbers. This doesn't restrict our x values. The second rule is that the output of g, which is g of x, must be in the domain of f. The domain of f is all real numbers except 0. So we need to ensure that g of x is not equal to 0. This means we must solve the inequality g of x is not equal to 0, which is x squared plus 3x plus 2, not equal to 0. Factoring the quadratic, we get x plus 1 times x plus 2, not equal to 0. This gives us the restrictions that x cannot be negative 1 and x cannot be negative 2. Since the first rule didn't give any restrictions, our domain is determined entirely by the second rule. The domain of the composite function is all real numbers except negative 1 and negative 2. This shows that the domain of the simplified expression 1 over x plus 1 x02 is the domain of the composite function, provided the domain of g imposes no additional restrictions.